Have you ever just stared at a long algebraic equation and thought, what does this actually mean? Well, what if I told you there's a simple, visual story hidden inside all those numbers and letters? Today, we are going to pull back the curtain on one of the most fundamental ideas in algebra, the zeros of a polynomial. We're going to turn that abstract math into something you can actually see.
So here's the plan. We'll start with a super quick refresher on what polynomials even are. Then, we'll figure out what a zero is in the world of pure algebra. And after that, this is where the fun really begins. We're going to translate that idea onto a graph, uncover the secrets of the classic parabola, and finally, discover a really powerful rule that ties it all together. All right, first things first. Before we jump into all the cool visual stuff, let's just make sure we're all on the same page. We're going to do a quick recap of what a polynomial is, and we're going to focus on just one key idea. And that one key idea is its degree. Now, it might sound a little technical, but I promise it's super simple. The degree is just the highest exponent you can find on a variable in the whole expression. And this one little number, it tells us a ton about what kind of polynomial we're dealing with. For example, if the highest power of x is just 1, the one we don't even bother writing, we call it a linear polynomial. And you should think line, because as you're about to see, that's exactly the shape it makes on a graph. Now, if the highest power is a 2, we've got ourselves a quadratic polynomial. The name quadratic actually comes from a word that means square, which makes total sense, right? It's all about that little squared term. And you guessed it, if the highest exponent is a 3, we call it a cubic polynomial. Each of these degrees, 1, 2, and 3, is going to create a totally different kind of picture, which is exactly where we're headed next. Okay, now that we're all warmed up, let's get to the main event. What on earth do mathematicians mean when they start talking about the zero of a polynomial? Let's use this quadratic polynomial as our guinea pig. We'll call it p of x, which is really just a fancy way of saying, hey, here's a polynomial, and the variable we're using is x. Now, what's really cool is what happens when we plug certain special numbers into this thing. Let's just try replacing every single x with the number 4. Okay, so we get 4 squared, that's 16, minus 3 times 4, which is 12, minus 4. And would you look at that? It all adds up to 0. And that, my friends, is the secret. A 0 is just any number you can plug into a polynomial that makes the whole thing equal 0. So, because p of 4 equals 0, we can officially say that 4 is a 0 of this polynomial. It's like the magic number that solves the puzzle. So, that's great and all. A 0 is a number that solves an equation. But what does that actually look like? I mean, if we could draw a picture of this idea, what would we see? This is where it all clicks. We're about to build a bridge from that abstract world of algebra to the very real, very visual world of geometry, just by looking at the graphs. Let's start simple again with our linear polynomial, y equals 2x plus 3. Now, if you solve this algebraically, set 2x plus 3 equal to 0, you'd find that x equals negative 3 over 2. That's its 0. Okay, now let's graph it. And as we expected, we get a straight line. And here it is, the big reveal. That algebraic answer we found, negative 3 over 2, isn't just some random number, it's a location. It is the exact spot on the x-axis where our line crosses. The algebraic 0 is literally a geometric crossing point. Okay, now we're getting somewhere. Let's take this awesome new insight that a 0 is an x-axis crossing point and apply it to our more interesting degree 2 polynomials, the quadratics, and see what their graphs can tell us. So quadratic equations don't make straight lines. They make these really cool curves called parabolas. And whether that curve opens up like a U or down like an N is super simple. It just depends on whether that first number, the one in front of the x squared, is positive or negative. So if a 0 is where the graph crosses the x-axis, how many times can a parabola do that? Well, in our first case, the curve can swoop down and cut through the x-axis in 2 completely different spots. This means the polynomial has 2 distinct zeros. What's another possibility? Well, the parabola could come down and just kiss the x-axis at its very tip, its vertex, and then turn right back around. It only touches in one single spot. So this polynomial has exactly 1 0. And finally, it's totally possible for the parabola to be floating entirely above the x-axis or maybe entirely below it. It never crosses at all.
In this situation, we say the polynomial has no real zeros. So what's the takeaway here? A quadratic polynomial, which, remember, has a degree of 2, can have 2 zeros, or 1 zero, or no zeros at all. But what's the absolute max? What's the most it can ever have? It's 2. A degree 2 polynomial can have at most 2 zeros.
I think I'm seeing a pattern here. This is getting pretty interesting. So for our last section, let's zoom out and see if this rule holds up for polynomials of any degree. Just look at this. A linear polynomial, degree 1, has at most 1 zero. A quadratic, degree 2, has at most 2 zeros. And it turns out, a cubic polynomial, degree 3, can have at most 3 zeros. I mean, the pattern is just staring us right in the face. And that brings us to our beautiful, simple, final rule. For any polynomial you can dream up, its degree, that highest exponent, tells you the maximum number of zeros it can possibly have. In other words, the degree tells you the maximum number of times its graph can cross the x-axis. It's just a perfect connection between the algebra and the geometry. So we did it. We found the zeros. They're the x-intercepts. But this just opens up a whole new fascinating question, doesn't it? We know these zero values are special, but are they somehow connected to the other numbers in the equation, you know, the coefficients? Well, that sounds like a story for another time.